All right, so first of all, we're going to talk real quickly about Bohr's atom. Bohr's atom. So in Bohr's atom, we talked about Bohr's atom being like a nucleus at the center, and then we arrange energy levels around it. Nick?
Is there going to be a lab this week?
Yes, there is. We're going to do pre-lab on Wednesday and then lab on Thursday. And the lab won't be due until next week.
That's good.
Okay. All right, so Bohr's atom. Okay, so this is a quantum mechanical model. So when we say quantum mechanical model, what we're saying is it's based off of quantities of energy, or discrete quantities. That's the whole quantum mechanics. That describes an electron as only having certain possible energies. So it's only possible to have certain energies. And so we looked at a model of this the other day on a little computer simulation, if you remember that. And light would come in and boost the electrons up, and the electrons would fall back down, they give off light. Does that sound familiar? A little simulation, okay. And so at the center here, we have a nucleus. And around that nucleus, we have energy levels. So I need to back up, Gary?
You're good.
Okay. Thank you. Boy, this is a lot easier to do on the board than it is this thing. Let me do this again. I just don't like the way that looks. Okay, let's try this. Okay. Okay, so I'm just drawing some rings around here. Okay, and this would be n equals 1, n equals 2, and n equals 3. So I'm calling those n. And n is the energy level. So n, the letter n, is energy level. Okay, so that is energy level, and possible values are 1, 2, what's this symbol here? Infinity. Okay, and to keep in mind, these are they're integer values. So what are integers?
Real numbers.
Yeah, real numbers are whole numbers, right? Integer values only. So there's no 1.5. There's 1, 2, 3, 4, 5 counting numbers. Now, in all seriousness, we usually don't have to go up much past, say, the 7th energy level. And the reason is this: if we talk about electrons in their ground states and the lowest energy levels they can be, 7 energy levels is enough to describe that whole periodic table. Now, the complicated thing is when light starts striking these electrons, they jump to higher energy levels. Okay? And they can jump up to an infinite number of energy levels. Right? So that's kind of confusing. What's infinite energy level? Infinite energy level basically means the electron has left the atom. You follow me? It's been ionized. And where is that electron? It's away from that atom. It's not part of that atom anymore. So it's someplace in the universe, but we don't know where. If we can give it an energy level, then we know the amount of energy it is because of that energy level. So a couple terms I've been throwing around here. One was ground state. Ground, like getting in on the ground floor. Ground state. And that's an electron at the lowest possible energy level. An electron at the lowest possible energy level. And if it gets struck with EMR, it can be raised to an excited state. And so that is an electron above ground state. An electron at an energy level above ground state. Yep.
What's the area?
Electromagnetic radiation. An electron at an energy level above ground state. So if you remember that little simulation I showed you, the electron started out at the lowest energy level. We hit it with light and we could boost it to a higher or excited state. And then eventually that electron dropped back to its lowest possible state, which would be ground level. Okay, ground state. Okay, energy of an electron. Oops. Energy of an electron. Okay, now I'm going to give you this little equation here, and I'm going to be straight up with you. This is not the one I'm going to be asking you to do calculations for. Right? We're going to be more interested in changes in energy, because that'll let us predict the color of light that's going to be emitted. Yep.
Could you go up like one line?
Yep. Okay. So, again, this is just one of those things I just give to you and you kind of got to accept it. But this is because people did some experiment and they found out that this was the relationship. Okay.
Is that 2 squared?
Z.
Oh, Z.
Yeah. Okay, so Z squared over N squared. So somebody found this out. So this can tell us the energy that an electron has. And that's useful, I suppose, but what's more interesting or more useful is if we find out how much an electron has when it's excited, and then how much it has when it goes down to a lower state, and that difference is the amount of energy that it's going to lose or gain, either boosting up or jumping down. Follow me? I hear them, don't see it, but it kind of lit. Try this again, right? So this will tell us how much energy an electron has. Great. But if I know how much energy an electron has initially and how much it has finally, I can figure out the difference between those two energies. And if I know the difference, that difference has either been absorbed from light or emitted as light. And now if I know the energy, you have an equation for energy of a photon. Now you can plug in here and now you can get out things like frequency and wavelength. So you see how this one's going to relate to this. This delta E is that E. Okay. So let's just look at it. So Z is equal to the number of protons in the nucleus. Now if you notice here, that's kind of like where that 1 is sitting. And the reason that there's a 1 here and Z here is because when we do our calculations, we're going to base it all off of hydrogen. And hydrogen would have 1 proton, and 1 proton squared would be 1. If it were helium, I'd have to put in 2 squared here, and that would become 4. But we're going to confine it just to hydrogen. Okay? So that's the first thing, and then the second thing is N is energy level. So that's how we could calculate the energy of an electron, but like I said, I'm not gonna try and pull any punches here. Just saying, I'm gonna ask you to solve the change equation.
So for the like the energy of a photon,
Yep.
for n, if is it plus or negative if it's endothermic or exothermic?
Okay, yeah, actually it is. So, good question. Okay, so a couple things here, and it made me think of something too. All right, so one thing to your question. If you solve this equation and it comes out positive, it means that the atom has absorbed the energy. And if it comes out negative, it has emitted the energy, right? Just like exo and endothermic. One thing I never really thought to even mention, I can't believe I never did, but this is energy level, N. What's that N?
Moles.
Not moles, you're close. It's number of photons. Okay, and that's in your notes. It's the number of photons. So if there was one photon of light, that would be 1. If you're talking about a mole of photons, that would be 6.02 times 10 to the 23rd. So that's number, that's energy level. Okay. Yeah.
Just out of curiosity, is that negative 2.178? Does that have some kind of fancy name? Like
Actually, it's let me think of the name of it. It does have a fancy name. I think I might have it written in my AP notes. Let me see. Yeah, it's the Rydberg constant. I forgot the name of it. Rydberg. R-Y-D-B-E-R-G. Rydberg. Okay. Now here's what I want you to be able to do. Change in energy of an electron in hydrogen. Now the reason we confine our studies here to hydrogen is, first of all, that's what Bohr did. Bohr was talking specifically about hydrogen. But he said basically everything that is true of hydrogen is more or less true in every other atom too, as far as these jumping energy levels. Okay. Okay, so let's say example. Oh, I'm gonna back up too. I think I like what you said too much already that I want to put it in there. So Ethan, oops. Come on, man. What? You don't want me to do that? What? What?
Oh,
What was that all about? Alright, is that not gonna let me do that? Are you gonna do that difficult? What? Looks like it's trying to let me do it right. It's just like, what is that? All right, well this, maybe I'll do it like this.
Be given what?
Let's do this. Okay, and I want to put here, this is what Ethan said. So if it's a positive, we'll say EMR absorbed. And if it's negative, we'll say EMR emitted.
what is EMI?
Electromagnetic radiation. Okay, so we'll do an example and then we'll just go over some homework. Good there? Okay, so let's say, this is the kind of thing we'll have to do. Calculate, oh, no, I didn't do what I did. Not an example yet. So here's the equation you need, and that's the one that's up behind me over here. Delta E equal to negative 2.178 times 10 to the negative 18th joules times the quantity 1, because we're talking about hydrogen, over n squared final minus 1 over n squared initial. Okay, now we're going to do an example. So basically what I'm going to do in this example is I'm going to give you what the electron does, what energy levels it jumped from and to. So if I know the energy levels that it started at and ended at, I can do this whole calculation and get delta E, which is an amount of energy. And if I know the amount of energy, I can plug it back into this equation. N, well, that's one photon because we're talking about one electron. H is Planck's constant. I can solve for nu, frequency, or N is the number of electrons, 1. Constant, speed of light. I can solve for lambda, solve the color of light. All right, so here's an example here. Okay, calculate the wavelength of light. Calculate the wavelength of light emitted when an electron moves from n equals 6 to n equals 1. Or, I'm sorry, 2. I want to do 2. Come on, 2. To n equals 2.
Bless you.
Okay. All right, so let's see. So we have an equation. Let's see. We're solving for wavelength is what we want to know. We've got an n equals, or n. We have an n initial equal to 6, and we have an n final equal to 2. Okay, so again, what I'm going to do is, I don't have wavelength in that equation, but I'm going to solve for final initial, get this, and that's going to give me delta E. And then once I have that, I can solve this for lambda. So I'm going to solve E of a photon equals NHC over lambda, solve for lambda. Okay. All right, so let's see. So we're going to have delta E is equal to negative 2.178 times 10 to the negative 18th joules times 1 over 2 squared minus 1 over 6 squared. So that's final and initial. Okay, so delta E equals negative 2.178 times 10 to the negative 18th joules times. Now what I would do is take the time to, don't mess with fractions. I know you got calculators to do fractions. We don't do fractions because fractions suck. Decimals are a lot easier to deal with, okay? So what I would just do is take 1 divided by 2 squared, or 1 divided by 4, and turn that into a decimal, and I'm going to get 0.25 minus 1 over 6 squared is 1 over 36. Take in your calculator, 1 divided by 36, and I get 0.028. And then if I go ahead and subtract those numbers and then multiply by that negative 2.1, I'm going to get negative 4.84 times 10 to the negative 19th joules. And this right here is telling me EMR is emitted. If I got a positive, it would have been absorbed. What's that? How'd I get negative?
19.
Negative 19? Well, this number is going to come out less than 18, or less than 1. And so when I multiply that, it's going to reduce it a little bit.
You multiplied those two by the 2
No, I took 0.25. You got to do order of operations. You got to do what's in parentheses first.
Yeah.
So 0.25 minus 0.028
times the negative 2.
times the negative. Yep. All right, so now we can plug into energy of a photon. Oops. Energy of a photon is equal to, well, I'm going to want to use the form NHC over lambda because I want wavelength. That's what I'm looking for. So I can rearrange this, and since everything's multiplied, can't you just swap those two terms? You Okay, so I'm gonna swap those. And I'm gonna get lambda is equal to NHC over E a photon, which we calculated. So lambda is gonna be equal to 1, because we're talking about one electron moving. If there's one electron, there's one photon. One photon makes that one electron jump up or down. One photon comes from one electron moving up or down. So that's 1. Planck's constant, 6.626 times 10 to the negative 18th, or negative 34th, sorry, joule seconds, times speed of light, 3.0 times 10 to the 8th meters per second, all divided by the energy of that photon, which we got to be negative 4.84. Now wait a second here. If I put in a negative, isn't that wavelength going to come out to be negative? There's no such thing as a negative length. So when I plug in here, I want to ignore a negative sign. Now I'm proactive enough right now because I know that's what's going to happen. So I remove the negative sign now. All right? Let's say you didn't see that and you go through, do the calculation, and you get a negative wavelength. You should start to think, well, why am I getting a negative wavelength? Well, the reason is you put in a negative energy. There's no such thing as negative energy either. The negative just tells us direction. Okay? So you got to be careful with your signs again. That could be an issue. So we're just going to put in absolute value here because that's all we need is the absolute value. So that's times 10 to the negative 19th joules. And so when I solve for lambda, I get 4.11 times 10 to the negative 7th meters. Okay. So if that was a wavelength of light, that's right around that purple light we've been talking about, because that was 400 nanometers. It's just like a slightly more towards the blue of the purple.
It's 1 because it doesn't mention how many there are.
No, it's 1 because this is talking about space 5, 6. Okay, here's my nucleus. We had an electron here, and it's dropping down to here. And what it does, it's going to give off a wavelength of light. So that's one electron dropping, making one quantum drop, or drop in energy levels, and that's going to give off one photon of light. So you get one photon of light boosts one electron drops, gives off one photon.
Would this equation work if you had 2 electrons? Like
If you did have two, if 2 electrons did this, then you'd plug in 2 there. Yep. And the energy would probably be double. Yeah.
Will it always be 1?
No, not necessarily. What if I said a mole of electrons? 6.02 times 10 to the 23rd. And you got some homework problems that were like that, actually.
Where did the 1 come from?
It's the number of electrons, or number of photons, I should say. There's just one photon there. You okay with this? I know you got a quiz coming up quick, but do you guys realize this is not that bad? I mean, it's 1, 2, 3, 4 equations. That's it. Right? As long as you know standard units and can do some basic conversions, that's all there is to it. Let's go over